So let's finish up chapter 15. We are going to skip the page on mixtures of acids. I usually take that out for a little bit behind. That's not a problem. We can start with then acid-base properties of ions. You guys encountered this in the pH lab, which was like a month ago or whatever when we actually did that. When it is an ionic compound, say like calcium nitrate here, when it dissolves, you have positive ions and negative ions floating in the solution. Either one of those could have an impact on the pH of the solution. What we need to figure out is how each of those ions behave. And we'll have a couple of rules here that'll help with it, but we're going to have to go sort of one at a time. So let's start with anions. There we go. Turns out that anions, the negative ions, will usually either be pH neutral, and we say pH neutral, we don't just say neutral because a neutral anion doesn't make sense, right? So we'll say pH neutral, which means it has no effect on the pH of the solution, or sometimes they're weak bases. But to figure out why that is, we need to answer what these anions are the conjugate of. So chloride, Cl minus, is the conjugate something of HCl.
Base.
It's conjugate base, because HCl is an acid. Okay. When something acts as a base, it gains a proton, an H+. So chloride is the conjugate base of HCl. Fluoride is the conjugate base of HF. Okay. Now, chloride and fluoride actually behave very differently in water because of the conjugates that they sort of come from. Okay. What would we consider HCl?
Strong acid.
That is a strong acid. But HF is a weak acid. Okay. So when we have a strong acid plus water, what happens? How would I finish this equation? Single forward arrow, making what?
H3O.
Hydronium and
Cl negative.
chloride. Okay. How would that be different with HF? That's equilibrium, forward and reverse. Same type of products. Okay. So, let's then draw a little divider here. Now that we know that, okay, we produce chloride ions and hydronium ions, okay, as a result, just as a forward reaction. Okay? There is no reversing, so a chloride cannot combine with a hydronium to reform HCl, but fluoride can combine with hydronium to make HF. Okay? That's important. That's the big difference here. So when we're talking about what chloride and fluoride actually are, we need to say chloride plus water and fluoride plus water. Okay? So it doesn't have any H's to give up. The only thing it could possibly do would be to take an H away from water, right? The products would be HCl and hydroxide. Products would be HF and hydroxide. Okay. But then the question is about the arrows here. Okay. And I'll give you a hint. Look at what happened over here. Chloride is formed from just HCl with water. Chloride and hydronium will not react. There is no reverse reaction here. Okay? So do you think it's even more likely or even less likely that chloride would react with water? I think it's less likely. Hydronium is the essence of acid, right? That is a thing that, if anything, would give up an H, hydronium would. Okay? So what do you think actually happens here? Forward arrow, reverse arrow, equilibrium. Yeah, if anything, it would be like a reverse arrow. In other words, chloride and water, if you have chloride and water, it will just be chloride and water. Okay? If you have HCl and hydroxide, that will make chloride and water. Okay? Fluoride and water, though, since this was in equilibrium, fluoride ions can remove an H from hydronium. Okay? Fluoride ions could also remove an H from water, probably to a small extent, but it's not impossible. So that will also be equilibrium arrows here. Okay? So I think what we need to get out here is that pretty much no reaction from okay. All right, so
that's just kind of like the proof that the arrow only goes one way.
pretty much. Pretty much. If chloride is not even a strong enough base to get an H from hydronium, there's no way it would be a strong enough base to get an H from water. In other words, okay? So that's one way of thinking of it. Another way of thinking of it is that that forward reaction is irreversible. Okay? If chloride could get an H from anything, it would form HCl, which is a strong acid. It would just break right apart again. Okay? So strong acids don't get formed as products. Strong acids are reactants, right?
How do you form strong acids then?
It can be formed not in an acid-base reaction, but it can be formed in an oxidation reduction reaction. If you have an even more powerful oxidizing agent, you can make it that way. So sort of a way that circumvents the proton transfer. Okay. So anions that are conjugates of a strong acid, that would describe chloride, right? Chloride is the conjugate of HCl, a strong acid. In a pH sense, what does that mean about chloride?
Chloride.
Low pH.
It is pH neutral. Yeah.
Because it can't accept hydrogen.
It cannot accept, that's a great way of putting it, it cannot accept a hydrogen from really anything, especially not even water. Could accept a hydrogen maybe from a stronger acid than HCl, but in water that's irrelevant. Okay. So, anions that are conjugates of strong acids are pH neutral. Okay? Cannot accept a proton from water. Anions that are conjugates of a weak acid, okay, like HF here. HF is a weak acid. Here is its anion. What is this fluoride acting as right here? A base. What kind of base? Weak base. Okay. So that was our little statement up at the top. Anions will usually either be pH neutral or a weak base. They're pH neutral if they're the conjugate of a strong acid. Okay? Because strong acids just break apart. We can't make strong acids from an acid-base reaction. Okay? We can make weak acids, however, at least to some extent. Okay? We're going to do the same analysis with cations. They'll usually either be pH neutral or a weak acid. Okay? To do that, we're going to talk about the same kind of bases that could produce these cations. Okay? Na plus is the positive ion in a strong base, right? Sodium hydroxide is a strong base. Okay? It's not necessarily like a conjugate, but it is the positive ion that is in a strong base. Okay? So, NaOH and water, that's just sodium ions and hydroxide ions. And the water molecule really isn't part of it. The NaOH just splits into Na plus ions and OH minus ions. Okay? Whereas NH4 plus is the conjugate acid of NH3. NH3 is a weak base. So if we draw equilibrium arrows, if NH3 is a weak base, it can accept a proton from water, making NH4 plus and hydroxide. Such that we could imagine NH4 plus with water now making what two products? What's about the only acid-base reaction that could happen right here?
NH3.
Yeah, we're not going to have NH5 2 plus. That doesn't make sense. We're going to do NH3 and hydronium. H3O plus. Okay? And because NH3 is a weak base, that can be formed in reactions. Okay? Whereas this similar type of thing would not happen with sodium. Okay? For a couple of reasons. Okay? We could possibly imagine something like sodium hydroxide and H plus. Okay. You could possibly imagine something like that. But again, here's sodium hydroxide, a strong base. This is not going to be an equilibrium. It's not going to be a forward arrow. This is actually going to be a reverse arrow, just like up above. Okay. So the key here is if we have some ion, and if when it reacts with water, it makes a strong base or a strong acid, then that can't happen. It'll be the reverse reaction. Okay? Strong bases and strong acids are not good products. They're reactants in acid-base reactions. Okay? We don't make them. As soon as we make sodium hydroxide, it would immediately react with that H plus, and we'd go back that way. Okay? So where's our little rule here? Sodium is the positive ion in a strong base. That means the sodium ion would be considered what of these options? Yeah. The sodium ion, it can't really react with water. Okay? So it's pH neutral. The ammonium ion can react with water. It acts as a what? Yeah, it acts as a weak acid. We know it's a weak acid because we can write a plausible equilibrium that produces hydronium. Okay? Equilibrium produces hydronium. That means NH4 is a weak acid. We could have said the same thing up above about the fluoride ion. An equilibrium that produces hydroxide is a weak base. Okay. So I think probably the best way to think of it is that if the ion reacts with water, if it makes something strong, that is not going to happen. Okay? If the ion reacts with water to make something weak, then that's an equilibrium. Okay? You'll have some of this and some of that. Okay? When the ion reacts with water, whatever else it produces, that tells you if the solution is acidic or if the solution is basic. Okay? So, let's summarize. What are some common pH neutral ions? Well, we only sort of memorize a certain number of strong acids and strong bases, right? And those are the ones whose conjugates or whose relatives are the pH neutral ions then. Okay? So the pH neutral anions, right? Those are conjugates of strong acids. Okay.
So most of the halogens minus fluoride.
Yep. So chloride, bromide, iodide, not fluoride. Okay.
Sulfur?
we're going to come back to sulfate. I think I have because sulfate actually has 2 protons, or sulfuric acid actually has 2 protons to it. That complicates things a little bit. So we'll come back to sulfate.
Phosphate.
But what are the other? Phosphate is a weak acid. Phosphoric acid is a weak acid. So what were the other strong acids?
Get out of my mind, SO4.
Come on. Yeah, sulfuric acid. And then there's 2 more. Nitric. Okay, so nitrate.
Yeah.
Yep. And 1 more. Yeah, perchloric. So ClO4 minus. Okay? And I think the best way to think of it is that they can't be bases.
You're too wimpy.
Yep. It would produce a strong acid. If they accepted a proton. Okay? The reason acids are strong acids is because the connection between the H and the anion is loose, right? HCl has a weak bond between H and Cl, so it gives away its H's. That means it's less likely that a Cl would accept an H. Okay? The pH-neutral cations come from the strong hydroxides. Which, do you remember where those were? Which hydroxides were the strong bases?
Sodium.
Yeah, so the group 1, right? So lithium, sodium, potassium, and group 2, calcium, strontium, barium. Okay. Okay.
No exceptions in that one.
I don't think so. I mean, I didn't list them all, but those are common examples. Okay. All right. Most other anions serve what purpose? Have what effect on the pH of a solution?
Weak base.
Yeah, most other anions are weak bases. Okay. Accepting an H plus would make a weak acid. And that's reversible. Okay. Accepting an H plus up here would make a strong acid. That does not happen. It's not like forward-back reversible. It's just totally backwards. Okay. Most other anions are weak bases. Most other cations are weak acids. Either donating an H plus or accepting hydroxide. That's sort of the opposite of donating an H plus, but that can happen with metal cations. Would make a weak base, which again is reversible. Okay, so other just bare metal cations, things like aluminum or iron, iron 2 plus or aluminum 3 plus or something, those would make aluminum hydroxide, which is a weak base. The only strong bases are the group 1 and 2 hydroxides. Okay? If it's different, if it's not just a metal cation, if it has H's to get rid of, we could get rid of an H, and it would make a weak base in that case. That was like what we saw with ammonium on the last page, right here. If ammonium, that has an H to get rid of, that makes NH3, which is a weak base. Okay? So, let's take a look at these ionic compounds. Let's first separate them into ions, and then determine, first of all, whether any of those ions are pH neutral. Okay? and then whether the remaining ion is weak acid or weak base. So, for instance, if I was doing this first one, let's separate into ions. Al3 plus 3 bromides. Okay. Are either of those pH neutral ions?
Or wait, we have bromide.
So, cross out the pH neutral. Right? Bromide is pH neutral because it comes from HBr, which is a strong acid. Okay? Aluminum is not neutral because aluminum hydroxide is not one of the strong bases. So, the solution of aluminum bromide would be what overall? Acidic, basic, neutral? Anything? Look at what most other cations do.
So that make it acidic.
Yep. Acidic because of the aluminum ions. Okay. Cations are usually acidic unless they're a cation that came from sodium hydroxide or calcium hydroxide or something like that. Those are just neutral. Okay. So try to do that with the other ones. Break them into their 2 ions. I might need to help you a little bit with sulfate, but we'll get there. So break each of those into its respective ions. Cross out any pH neutral ions, and look at the impact that the other one has. So first of all, what do you guys think about strontium chloride?
Is it?
Are there any pH neutral ions here?
Yes.
Okay. Strontium?
Yes.
Ooh, look at this. Strontium is group 2. See, strontium hydroxide would be a strong base. So forming strontium hydroxide doesn't happen. So, what does that mean about that solution?
Neutral.
That's actually pH neutral. Okay. The ammonium ion and the iodide ion. pH neutral ions here.
Iodide?
Yep, iodide is. So this solution is, this is acidic. NH4 plus has a proton that it can donate. Okay. Doing so, it would produce NH3, which is weak. So that's allowed. Okay. All right, let's look at this one. So essentially 2K plus and sulfate. Okay. So now is our chance to talk about sulfate, because H2SO4 is a what? Strong diprotic strong acid, which means it will full forward arrow, but not at losing both of them, it turns out. It's just strong for the first one. So HSO4 minus, okay, would be sort of the first step. So this is a forward arrow. Okay. Every sulfuric acid will produce HSO4 minus after it gives away a proton. Okay. But then after that, it's an equilibrium. O4. Okay. All right. So, what does HSO4 minus act as right here in this sort of sequence? If this is just totally a forward arrow, you can't go that way, can only go that way. What does that mean HSO4 could be? What do you think? I mean, these aren't balanced. I haven't included the H's here, but
Say your acid.
so this is a weak acid because it's at equilibrium with sulfate. Okay, it's okay. Can HSO4 minus gain an H plus? No, because this is a strong acid. Okay, so HSO4 minus is not a base in any way, because if it acted as a base, it would make H2SO4, which can't go that way. Okay. Now over here, sulfate, over at the other end, what's the only thing it can do? It can gain an H, which makes it a, yeah, okay, so it's a weak one. Okay. So that's how that works. So HSO4 minus is a weak acid, the hydrogen sulfate anion. So that's unique because most of our other anions were either neutral or basic. Okay? It's uniquely acidic because it has another H to give away. Okay? And it's not basic at all because if it attracted a proton, you'd make this strong acid. Okay? So with that in mind, up here, K2SO4. So neutral on the K plus, right? Potassium hydroxide cannot form. Okay? And then we got sulfate ions over here, which that's the normal kind of thing that a anion would be. So what would this solution be?
Basic.
Yeah, this would be basic. Okay. Alrighty. K2SO3. You could do the similar sort of thing for sulfite. The difference here is that sulfite is a weak acid, so this can go both ways. Okay? So if you ended up with HSO3 minus, it could go either way, depending on the circumstance. We'll have to calculate that later on. Okay? But over here at this end, whether it's sulfate or sulfite, there's only one thing we can do. Yep, it can gain a proton, so that is also basic. Okay. Sodium and cyanide. Cross out what? Cross out sodium. So solution is basic. So what we're going to need to train ourselves to do now, from now on, with an ionic compound, okay, is if if one of the ions is pH neutral, which it actually usually will be, okay, if you're doing any kind of calculation with it, if one of the ions is pH neutral, we're going to ignore that for the sake of pH calculation and focus only on the ion that has an effect on the pH. So if the problem is a sodium cyanide solution, we're not going to set up our equilibrium table with sodium cyanide. We're going to set up our equilibrium table with Cn minus, with the active ion that's actually going to do something. Okay? So let's try it.